We're going to discuss the two different forces, conservative versus non-conservative forces. Conservative forces are forces that can possibly get us back the work that we put to act against them. For example, gravity, elasticity, and springs. Now, for a force to be considered a conservative force, it needs two criteria. The first criteria is that the force is conservative when the work it does on a moving object is independent of the path between the object's initial and final position. Basically, it means that the work being done is only dependent on the initial and final. Everything else in between doesn't really matter. Version 2 says that a force is conservative when it does no work on an object moving around the closed path, starting and finishing at the same point. Basically, if you do find the work done by a certain force and you get back to the original starting position, the work done by that force is zero. Let's look at some examples. So the conservative forces we have in this class is gravitational force, elastic spring force, and electrical force. Pretty much everything else is non-conservative. Static friction, kinetic friction, air resistance, tension, normal force, force done by engines are all non-conservative forces, and we're going to discuss why. So let's look at gravity. Gravity is a conservative force. If we look at the equation of the work done by gravity, the work done by gravity is mg times the height initial minus the height final. Another definition is work done by gravity is equal to the change in potential energy. Now, when you find the change in anything, it's pretty much the final minus the initial, meaning everything in between doesn't matter. So it already falls under that first criteria. And the path that it takes doesn't really matter. Meaning, if I drop a ball from rest from here, and the ball gets to this position, whether I drop it or I throw it and it follows this path, the change in potential energy is the same, meaning the work done by gravity is the same, meaning the work done by gravity is independent of the path taken, only the final and the initial matter. Now, version 2 for gravity. Gravity falls under the category of version 2 as well, because if you imagine a roller coaster in which friction is ignored, and the roller coaster takes this entire path all the way around, and it comes back here. If we try to find the work done by gravity, and we take the mass times the gravity, h initial, h final, when we take the initial height minus the final height, it's going to be zero because it ended up at the same height that it started. So in a closed path, the work done by gravity is zero. So it falls under the two criteria. Since gravity follows criteria 1 and 2, it is considered a conservative force. An example would be if you throw an object in the air and it comes back to you, or the work done by gravity would be conservative. If we look at a non-conservative force like friction or the motor of a car engine, it is not conservative. So imagine you run here, you turn around, and you end up back where you started. Okay, so you have a closed path. Now, if we look at the first criteria, work it does on a moving object is independent of the path between the object's initial and final position. And part 2 says it does no work on an object moving around the closed path. Now, since it's a closed path, you want to say like, oh yeah, the displacement is zero. That means if we do work is equal to force times the distance, which is the same thing as the displacement, times cosine theta. Since the displacement is zero, the work done is zero. That's not actually true, because the problem becomes that we can only use this equation if the force is constant. The force, even though we imagine the magnitude of the force as we run from this path all the way back, if we imagine the force that's allowing us to run to be this constant magnitude, the direction is not the same. As we run forward, the thing pushing us forward is the static friction of our shoes. But then when we start running back, static friction changes direction, meaning the force is not constant. So to find the work done by static friction, we would have to find the work done along this path, and then find the work done along this path. Now, for the first work done, for the first part of our trip, which is we working from beginning to the end, the force is pointing this way, the displacement, which we'll kind of symbol with this S, meaning displacement, is pointing in the same direction. So for the beginning part, you're doing positive work. But then on your return path, the static frictional force is pointing back. Your displacement is pointing back. So the work done here is positive. When we add up all the work, which is that positive work plus that other positive work, it's impossible for these works to cancel out. So therefore, it doesn't meet criteria 2. No work is done, and there is work being done because all you're doing is positive work. The same thing can be said if it had been an engine or the work done by friction. If we look at the same path, you run this way, and you turn around. Let's do it a little different. Let's say you're sliding a box, and you slide a box by pushing. Let's call this FP. Is pushing this box all the way across. And then in the second part, we grab the box and we push it back into its starting position. For the first part of our trip, the force is pointing this way, the displacement is pointing this way, so the work done is positive. For the second part of our trip, the force is playing this way, the displacement is playing this way, so the work done is also positive. It's not possible for these two works to cancel out because they're both positive. If we think of the friction that is acting on this box while we slide it. Now, as this box gets slid across the floor, there's a frictional, kinetic friction counteracting it. In the beginning, the frictional force is pointing this way, and make it in red so we keep it consistent. And the displacement is pointing this way, so the work is negative. So maybe the work will cancel out. But then on the way back, the frictional force is pointing this way, the displacement is pointing that way, so we end up doing negative work on our way back. So either way, the work won't cancel out because it will just end up magnifying the work. So all these are examples of how these forces fail to fall under both criteria. Therefore, they're not considered conservative force. They're considered a non-conservative force. Okay. And this is just further going on about how friction is a non-conservative force. Kinetic friction always does negative work because it's always pointing in the opposite direction of the movement, so it's impossible for the kinetic friction to ever cancel out because it's always going to be a negative number. Under normal situations, we always have a series of conservative and non-conservative forces acting on an object. As an object falls through the air, even though gravity, which is a conservative force, is acting on it, we also have a resistance force by the wind acting on it. When we look for the total net work is equal to all the conservative work being done plus all the non-conservative work being done by those non-conservative forces. And when we combine it with our net work equations, and we assume that the only conservative force, because at the moment we're not going to be doing springs and elasticity that much, we're just going to assume that the only conservative force we're going to dealing with is gravity. So all the conservative work is equal to the work done by gravity, forgot an equal sign, which is just negative change in potential energy. So when I rewrite the equation, instead of saying negative work, I'm going to say the change in kinetic energy is equal to the negative change in potential energy plus whatever all the non-conservative work is. So work non-conservative, if we rearrange the equation, is equal to the change in kinetic energy plus the change in potential energy. So if we wanted to find out what the work done by all the non-conservative forces were, we would just find the change in kinetic energy, the change in potential energy, and add it up, and it will tell us what the work done by those non-conservative forces. If we're talking about something falling, we would think about the force of gravity acting down on it, and then some kind of resistance force acting up. We can use this work to help us figure out what this resistance force was. So now we can start taking friction into account in all of our problems, which I'm sure you're probably excited about. The next slide just finds another equation in which we can solve our work non-conservative. Our work non-conservative is equal to our change of mechanical energy. Mechanical energy, pretty much mechanical energy, the formula for mechanical energy is equal to the potential energy of an object plus its kinetic energy equals its mechanical energy. And this is just a long derivative of it. So basically, work non-conservative is the final the final mechanical energy minus the initial mechanical energy. So if you can find what the initial and final mechanical energy is, you can find the work non-conservative. If there is no non-conservative forces acting on an object, then you should find out that the final mechanical energy is equal to the initial mechanical energy. So if the change in mechanical energy is ever zero, that means the only forces that are acting on the object are conservative forces, meaning things like gravity.